For the lab on heat flow, I assigned a problem where you're going to calculate the nature of the thickening crust on top of a lake. Most specifically, how is this lake freezing over? To work through an example that's related to this, let's consider the thickening crust that's on top of a lava lake. Much different thermal parameters, but the math is exactly the same. What you're going to need to do this is to be able to iteratively solve using the error function. And I've found the best way to do this is to run it through a spreadsheet program like Excel. You can do it any way you want. There are a number of different ways to get this done. But I'm going to do it in Excel as an example. So you can see I have an Excel sheet up here, and I want to figure out the solidification of crust of a lava lake after 1 year using the following parameters. I'm using a latent heat of crystallization that's 400 kilojoules per kilogram, a specific heat that's 0.84 kilojoules per kilogram degree Kelvin, and our difference in temperature, the outside temperature to the temperature of the lava, is going to be 1050 Kelvin, so 1050 Kelvin. The thermal parameters, besides the specific heat, are also going to be the conductivity. Conductivity is going to be 1.7 watts per kilogram degree Kelvin. And the density of basalt, I'm going to use 2950 kilograms per meters cubed. So that's the recommended value from the book. First thing I need to come up with is a kappa. So kappa, of course, is the thermal diffusivity. Slightly different than conductivity, and it's just taking the conductivity and essentially making it a little more manageable by running it through both the specific heat and the density of the material. So let's do exactly that. I'm going to put in kappa here to keep track of the units, and then I am going to set up my equation, and it needs to be the thermal conductivity. That's B6 divided by, and then I'm going to put in the parentheses for the denominator, rho times C. So that's B7 times B4 the way I have it set up. And that gives me a kappa of 0.00069. So I guess I'm okay with how it's leaving that. Need to think a little bit about the units that are going to be left off here in terms of what we have left when all is said and done. The dimensions of kappa are, because it's a diffusivity, meters squared per second. We use length squared over seconds for talking about diffusivities. Two ways you can get at this is, one, to think about what a diffusivity is and what it means in terms of moving materials or energy through a substance. The other way is to do some dimensional analysis on the units that we've used, because remember we took watts, kilograms per Kelvin, and we divided it by kilograms per meters cubed, and we also divided it by kilojoules per kilogram per Kelvin, and we end up with just meters squared per second. The seconds were retained from the watts. So I'm going to put in meters squared per second in my units, and I'll clean that up so that my square is actually a square. Another cheat you could use for that is just putting in a caret sign, but I'm going to actually make it a superscript so it's nice and official looking. All right, so there we go. That's going to be our kappa. With that, I've got everything I need to move forward, except getting time in the right units. So our kappa isn't a per second value. We're going to need time in seconds as well. So I'm going to convert 1 year to seconds. We're going to just use 365 for days. So I am going to put in an equal sign, and then our 1, or whatever is in that box, the 11, is going to be times 365 for a day. We'll use 24 hours in a day. So 365 days in a year, 24 hours in a day. And then I need to deal with the seconds and minutes. So in each hour, there's 3,600 seconds. So I'm just going to plug that in. So that's our time in seconds. 1 year is 3.2 times 10 to the 7 seconds. Or I could just put S. I guess that's more consistent with what I've done so far. So that's still our time. To solve this problem, we're going to need to use 4.141 from the book. 4.141 is going to have us find a lambda that we can use. Now, you can't just out and out find lambda. If you look at the right end of that equation, that's a mess. There's no solving for lambda here. Fortunately, there are some powerful tools you can use at hand to make some guesses at what works until you narrow it down. This is called iteration, when you keep solving and solving until you get close to the right answer. And computers are great at this. So that's why I'm going to call on my Excel sheet to do this. What do I need on the left side of that equation? I need latent heat of fusion. I need to multiply that by the square root of pi, and then I need to divide it by the specific heat, and then the difference in temperature in degree Kelvin. Make sure it's in Kelvin, although a difference in temperature won't make a difference in this. So let's set up the left side of the equation first. I'm just going to type in left here, and then I'm going to take my latent heat of fusion, and I'm going to multiply it by the square root of pi, and in Excel ease, pi is given by typing in pi with 2 brackets, an open and close one right after another, for reasons I don't understand. And then I'm going to put the denominator in brackets so it doesn't get lost. And in the denominator, I needed the specific heat, so I'm going to take that, and then I'm going to multiply it by the difference in temperature. So difference in temperature is right there in B5. Close that together, and I get a left side of equation that is 0.80383. Okay, what we're going to do now is try to guess what lambda is. So what I'm going to do first is just put in a lambda. It can be anything you want. I'm going to start with 1. Usually 1 doesn't cause too many problems. I wouldn't suggest using a lambda of 0. That may be more hassle than it's worth. Then I'm going to set up the right side of the equation. You've got to be very careful typing this in. So the right side of the equation is the exponential, so exp, and then you have to have a negative sign and then another parentheses so that you don't accidentally square this, and then you're going to take your lambda, the cell above it, and square that. So I'm squaring that, and I'm going to close that down. So I got 2 parentheses that enclose the exponential. Now I can go to the denominator. The denominator is just going to be lambda times the error function of lambda. Sorry, I do have to use parentheses for that. The error function of lambda. And then close that, and my whole thing should be enclosed together. With a lambda of 1, I get the right side equation to equal 0.43655, which of course is not the same as the left side of the equation. But here's where the power of Excel comes in. I'm going to click on B17 here and perform a what-if analysis. So I'm on the data pages, what-if analysis. I'm going to do a goal seek. A goal seek is just a built-in little program to change some things so that you can get to the right value. And what we're going to change is B16, our lambda value, to get a number that matches the number we had before. So I'm going to have to type in that number, 0.80383. So 80383, and the cell I'm going to change is B16. So there we go. It's going to try to get B17 to equal this number by changing the numbers it puts into B16. So it's going to disregard my 1 and start with some other numbers. This is called iteration. It's just going to keep cranking through it until either it resolves or goes through enough steps that it can't find a solution. So I'm going to hit OK, and just like that, it's going to calculate it out. So it decided the right lambda for this is 0.82759. Okay, the last step that we need to tackle is using 4.136 to find this thickness. What the book uses is Ym. This is the cooling thickness that we get from the Stefan problem. So let's see if we can get it to do that. Basically, I'm going to say Ym, and this is going to be in meters. We have kept everything nicely in the meter unit, so going to end up with meters when it's all said and done. And then Ym is going to be 2 times lambda, which we just calculated. So 2 times, okay, it helps if you put an equal sign before you start typing things in. 2 times lambda, right there. And then we're going to multiply that by the square root, SQRT, in parentheses, of our kappa, which you calculated earlier, times the amount of time that we've involved, and we have to use time in seconds, so we bothered to calculate that out. So if I've got everything together here, I'm going to take the square root of kappa times time. That's going to get rid of the time function, leave us with meters squared. The lambda is dimensionless, so we'll end up with meters when it's all said and done, because we're taking the square root of meters squared. And there it is. Should be 243, and I'm going to leave it at that. 243 is as good of answer I can get, because even though I sort of let everything go here, we've been dealing with 3 significant digits at most for any part of this. So going back to home, I'm just going to truncate that down, make it 243. So 243 meters is our thickness. You can, of course, change things if you decided, well, I'd rather see what happens after 2 years. Well, the spreadsheet's already set up for that. It becomes 344 meters. You could even make a plot of these things if you wanted to. So there it is. That should get you started on problem 437. The numbers are different, but the process is the same. Now, what you've done here with Excel, just quickly, is try to be organized about it. Make sure you're keeping track of your units. That's one thing that can throw people on these problems. This is sort of intermediate Excel use. So basic Excel use, I consider, typing in an equation or two. Intermediate Excel use starts to take advantage of the programming that's built into Excel to solve some problems. So again, the key to this was going to data and using the what-if analysis and goal seek so that we could iterate. The other sort of advanced or intermediate use of it is the use of the error function. That's not a freshman level problem right there. The error function is, of course, that approximation that allows us to do this curvature. And Excel does that math for you automatically. Hopefully this helps.